This is This Week in Science and Education, episode 35, the Canadian Light Source, recorded Tuesday, April the 12th, 2011. This Week in Science and Education is brought to you by Sheridan Institute of Technology and Advanced Learning. At Sheridan, students shine brighter. Visit SheridanShineBrighter.com. It's time for This Week in Science and Education, the show that talks about all things science-related, health research, information, and how to convey that information and bring it into today's classroom. On today's show, the Canadian Light Source. All that and more coming up next on This Week in Science and Education. Hey everyone, it's time for This Week in Science and Education. This is your host, Kevin Cougler, broadcasting today live from Sheridan Institute of Technology and Advanced Learning here in Oakville, Ontario. Interesting story on how this all came about, but long story short, I wanted to come down and see my partner in crime personally, Colin Jagoe, from the Core of the Panelists District School Board. Hey, Colin.
How you doing, Ken?
Good. Nice to see you here in Oakville.
I know, it's Oakville. I've never been to Sheridan before. It's been kind of interesting. Not a very interesting story. I'm just here for work for another reason and another spot. Picking up some science videos from a media display that's down here to feed into the board's media system. So it's been interesting, but I was able to squeeze away for a little while and come on over here and do the show with you. Good.
Well, I was glad to hear that you were here, and since you're in Peterborough, any chance where we can meet in the middle, you know, and,
absolutely.
Have a coffee or something is always a good thing.
Absolutely.
So good to do this today. And thanks to our kind hosts here at Sheridan Institute, by the way, as well, for kind of rolling with us at the last minute, finding a room for us. We really appreciate that. Let's get to our guests.
Sure.
Okay, so we have Rob and Tracy from the Canadian Light Source. I think we'll start with Rob. Rob, welcome to the show. Thanks for taking the time to join us today.
Oh, thanks very much. Great to be here.
Maybe we could start by just having you introduce yourself a little bit, talk about your role at the Canadian Light Source. I understand you're the Assistant Director in the Research Division there. Maybe talk a little bit about what that means and really what the Canadian Light Source is and what it's all about.
Okay, well, we are Canada's national synchrotron facility. We're a particle accelerator. That's the primary machine that we have in our building. We have a building that is the largest building in Saskatchewan. It's approximately the size of a hockey stadium, to give you a sense of scale. The main machine is 174 meters in circumference, and it's a particle accelerator. But unlike the stuff you're seeing from the Large Hadron Collider in Europe, or the recent stuff you might have seen from the Tevatron down in Batavia, Illinois, we don't actually do particle physics here. One of the sometimes unpleasant side effects for particle physicists is if you take a charged particle in a magnetic field at relativistic speeds, like you do in a particle accelerator, every time they go around a corner, you get radiation coming off. Now, for them, that's a problem for two reasons, because that's energy that's not going into their particle collisions, and obviously they want as high energy as they can, and also it can be a safety issue, so that's why those facilities are typically built fairly deep underground. And quite a long time ago, back in the 60s, people realized, well, actually, this is potentially an extremely useful source of radiation for doing experiments. Conventional X-ray sources are fairly low power. You can't tune the energy, you can't tune the polarization, but with a particle accelerator, you can do those things. So starting in the 1980s, people started to build particle accelerators optimized for making radiation for doing experiments. And when I say radiation, I mean pretty much the whole electromagnetic spectrum from the far infrared up through the visible and into what we call hard X-rays, which are highly penetrating. Canada has been trying to get into this game for quite a long time, pushing since the 1970s, and eventually the government said yes, and we have this fine facility. And one of the advantages of being late into the game is we can learn from what everybody else has done. As you possibly have noticed, I am British. This is not a speech impediment. And a lot of expertise is available from outside Canada. So we have what we call the third generation of synchrotrons, has been built in the last few years. We're one of the last ones to come online, which means we're one of the most technologically advanced light sources in the world. So you have radiation coming off your particle accelerator. What you need to do is then turn that into the wavelength you want, and the spot size you want, and really tune all the properties of the light so it's perfectly tuned to your experiment. So what we have is a series of, at the moment, 15 beamlines, which do exactly that. They take the basic radiation coming off the machine and turn it into exactly the kind of photons you want for your experiment. And my division is the Experimental Facilities Division, and we're the people that run the beamlines. And unlike most laboratories, sometimes people find it a little difficult to get their head around. 90% of the science that's done inside our building is not done by our scientists. So anybody from anywhere in Canada, in fact from anywhere in the world, is welcome to write a proposal to do an experiment at our facility, and we have hundreds running into thousands of people from all over Canada, all over the world, come to Saskatoon to do their experiments with our beamlines. And
really?
Yes, absolutely. And sometimes it's quite amusing because you think of all the reasons people come to Canada. I mean, particularly tourists. You think they come to see Vancouver and the Rockies. They come to see Niagara Falls. They come to see the CN Tower. But there's now a significant number of people from outside Canada, and the only part of Canada they've seen is Saskatoon, and that's because we're here.
Excellent.
I bet the Saskatchewan government loves that.
Absolutely.
You better.
Just a quick question, if I may, Rob. Some of our listening audience might be students who are in the higher grade levels, 9 to 12, and maybe thinking about science as a career choice. Maybe talk a little bit about how you got into this type of career, and maybe spread a little bit of insight into for students on how they can enter into physics as a career choice.
Well, I started off, what I really wanted to do with my life was become a military pilot. But neither my hearing nor my vision was good enough, so I had to find something else. And I grew up around very large aircraft. My father was military, and I was reasonably good at science, so I ended up going to college to do a degree in physics. And then looking around for something to do after that, it was suggested, well, you seem to be really interested in finding out about things, maybe you should do go to graduate school. So I went to graduate school and I started doing surface science, which mostly involves large vacuum chambers that are roughly about as big as I am now, and that was fun. And then somebody said, well, I've got an experiment coming up at the Synchrotron, which was about 40 kilometers from where I was working. And the thing about a synchrotron is it runs 24/7. So if you're going to take some researchers there, you've got to have bodies, you've got to have pairs of hands available around the clock. And he was new faculty, he didn't have many students, and he said, would you like to come and take part in the experiment? I said, sure, sounds interesting. I had no idea what a synchrotron was. And it's quite the feeling when you walk onto the experimental floor of a synchrotron for the first time. It's like really nothing else in a conventional laboratory. It's an enormous room the size of an aircraft hangar, or like I said, a hockey stadium. And the way the beamlines were set up there, you actually had to walk up a flight of stairs onto a gantry to look at the particular experiment we were going to work with. And from there, you got an overview of the whole facility. And that's the point I said, I want to work at one of these facilities. And I've spent my entire career bouncing around different parts of the planet doing pretty much that, either working at the facility or working in a laboratory that used that kind of facility. And it really came down to, I just followed what I was interested in rather than thinking, can I make a career out of this? It's like, this is fun. I'm maybe not going to make an enormous amount of money, but I'll probably be comfortable. But I get to do stuff I enjoy every minute of every working day. And not everybody gets to do that.
No, that's a great message, And I'm wondering, Rob, we have one of our education experts here who happens to know a lot about science. Do you think between the two of you, you might be able to talk Colin through how to draw the cyclotron here behind us on the whiteboard? Because we have this fantastic, do you think we could do that? I mean, it's round.
Okay, I think we can do that. We'll have a go.
Let's do that.
I could pull up the PDFs that I was looking at on the website earlier. And actually, while we're doing that, I did have some questions, because as I understand it, there's sort of, you've got the round part of the particle accelerator in the middle. So if you move that up, Kev, right? So,
okay.
And one of the questions that I had was, you talk about that when the radiation comes off, right? It's then shunted out through another path to where you have your experiments. My first question was, what's actually going around then? What elements? Is it protons? Is it hydrogen? Like, what do you put into the beam to then strip off the light?
Okay. Well, basically, it's electrons. I mean, you can build particle accelerators for any charged particle. And what I'm actually going to ask you to do is erase that diagram, and we're going to start again. All right?
Nothing but the best here from Beamlines.
I know. If you'd have planned it, you could have come up with a better idea. Okay, shoot.
All right. So what I want you to do is, instead of drawing a circle, draw a polyhedron, right? So with maybe a 12-sided polyhedron.
So it's like a stop sign with just more sides, right? Wow.
Yeah, it's a stop sign with more.
Yeah, no, I'm just describing it for Kevin. But I have a question now. Is that because it doesn't actually go in a circle? It goes in segments of straight line, and then you have like
exactly.
where it's curved?
Yeah.
Okay, all right.
In fact, Rob, you
the
talked to a
way
grade 5 student on how to do this yesterday, didn't you? So Colin should be able to handle it.
Yeah, I know. I got too much angles on here.
Maybe that works.
Okay,
That's not great.
we'll call that an artist's impression and just run with that. Okay.
Absolutely.
So in some ways, it's like NASCAR, right? You got straight sections and you got bends. Okay.
Yeah.
Now, anytime you have a bend, when an electron goes around the bend, the light comes off at a tangent to that bend.
Okay.
Okay.
All right.
So just draw a straight line coming off like that. Perfect.
So the light
That's
goes
great.
off. So this becomes then the light, and the electron itself keeps going.
It keeps going round. That's perfect.
Right.
Yes.
Okay.
Yeah.
Right.
Although I should point out that our electrons actually go the other way round. Although it's fun to notice that the British synchrotron I worked at, they went round in that direction, but in North America they go around the other direction. It's just like driving.
Yeah.
Is that like the water in the toilet bowl phenomenon thing, the hemisphere related thing?
Yeah.
So is light then taken off at every corner then?
Yeah.
It potentially could be. But then you run into the practical reality of trying to do science at a big facility is these things cost money, right? So you had the original budget of around $175 million to build a synchrotron with 7 beamlines. Now we can accommodate maybe 30 at a push, but you don't build them all at once. Because, I mean, first of all, then you have a facility that's going to all be obsolete at once. So we started with 7 beamlines. And then we went back to the Canada Foundation for Innovation and asked for more money. Go ahead.
Okay. So would a beamline be an individual spot where light is coming off then, or is it somehow combined into one spot?
No.
Yeah, it's an individual spot. I mean, the way to think about it, the light's coming off everywhere, at every bend, and most of it right now is just hitting concrete, because the synchrotron itself is inside a concrete enclosure.
Okay.
So if you want to take the light out and actually use it for an experiment, you have to build a beamline. And beamlines range from 10 to tens of meters long. They're all special order pieces of equipment. They typically cost between 1 and 20 million Canadian dollars. And you don't get all that money at once.
Yeah, no, of course not. Okay. Excellent. That makes a lot more sense to me now. Does that help you understand it, Kevin?
Yeah, that's good. Now tell me why this would be important in school. What would you teach the students with that?
Oh my goodness. Where would you start? I mean, first of all, you could talk in terms of classical physics of momentum, right? And how things generally travel in a straight line. And when you, I'm assuming when you then cause it to go somewhere else, you're losing some of that energy because you're actually, maybe you can explain it better than me. I just think that as you're forcing it to go a different direction, you're putting another force on it there, which is then causing it to lose energy. Is that sort of a way to describe it?
No, I think Tracy wants to jump in and say something here.
Please, Tracy.
I would like to point out that while you're right, there's an awful lot of physics that goes into producing this light, and that's a gold mine for physics teachers.
Okay.
Once the light is there, every other scientific discipline makes use of it to conduct their research. So each beamline is unique, and you will find chemists and biologists and archaeologists and geologists and lots of other ologists using the light to conduct their experiments.
This is a great time to introduce Tracy. Rob, would you do the honors of introducing Tracy to your left, please?
Sure. Hi, everybody. This is Tracy Walker. She's the educational outreach specialist here at the Canadian Light Source Synchrotron.
Thanks, Tracy, for that commentary. Did I spell cyclotron right, by the way?
That's cyclotron.
That's cyclotron.
That's a different word. We're synchrotron.
Synchro.
All right, nice.
Do you guys know what the difference is?
No, please tell us.
Okay. A cyclotron is, I mean, if you think about it, if you have a North Pole and a South Pole magnet and they're circular, and you put an electron inside there, it's going to go around in a circle, right? And, you know, and physicists typically have very little imagination whatsoever. So back in the sort of 1920s when these were being developed, everything was a something tron, right?
Right.
But, you know, back then, I mean, there was a lot more classical education going on. So you think about, I think it's the Greek word for circle is cyclo.
Okay.
So if you like, it's a making things going round in circle machine, which in physics terms is a cyclotron, right? And then, and obviously, the larger you build one of these cyclotrons, the higher energy you can get. And obviously for high energy physics, that's good. But it gets to the point where making big magnets becomes really difficult. So instead of having just two very large magnets, you have what you show behind you, which is a series of straight sections and bending magnets. And those bending magnets work all together. So it's a synchronous cyclotron, right? And of course, that's too stupid even for physicists, so that got shortened to synchrotron fairly early on.
So I spell that then S-Y-N-C-H-R.
Rotron, yes.
Rotron. Okay.
Now, I'm thinking about the light.
Excellent.
Yeah, you got it. I'm thinking about the light again, okay? Because in typical high school physics, right, or well, even earlier than that, we talk about electrons and different levels of orbits, and when an electron drops from one level to another, there's light given off. Is there any way that we can relate that in terms of light being given off to how light is given off here? Is there a way to draw that connection?
It's not that easy. I mean, basically, this is a relativistic effect. But if we talk about what we do with the light, it ties absolutely right in. Okay. So one of the experiments we do is called X-ray fluorescence, and we can do maps with X-ray fluorescence. So what you do is you take the beam, you shape it into an extremely small spot between 1 and 5 microns in size, and you put that on the sample. Now what's then going to happen is the high energy X-rays will cause ionization of the atoms in what you're looking at. Then, because it's high energy, when those core holes decay, so when exactly that happens, you get, you know, maybe your 1s electron's been kicked out of something heavy like iron, and maybe a 2p electron drops right down in. You get an X-ray photon given off, and you can measure that X-ray photon. And of course, every element has a different characteristic set of X-ray lines that come off in that process. So what you have is a fingerprinting technique. So you say, okay, we're going to point the beam at the sample. We get these X-rays coming off the sample. We measure the spectrum. That tells us what is it in that point. Okay. Now that's one point. Then you say, okay, well, we could try and move the beam, but actually, because that would involve moving the synchrotron, that's kind of hard. We actually move the sample. So what you do is you track the sample in a raster-type pattern, and at each point, you do a map of, well, what elements are in this sample, and you can build up elemental pictures of what elements are present in a sample, and you can do it on the micron scale.
Okay.
So it's a way of not just doing microscopy, but doing spectroscopy at the same time, which we call spectrum microscopy.
Yeah, I was going to say it sounds very similar to spectroscopy, like you'd use in a gas chromatograph or something like that. Just to, instead of burning it to get the light, you're hitting it with something and then watching it fluoresce.
Yes.
Yeah.
And the really nice thing about being able to do that is that tells you what elements are present. What you can also do, you can do X-ray diffraction, right? So you can do diffraction at the same time on the same spot, and that tells you the crystal structure of any material that might be in there. So if you know the structure and you know the elements, then you've got an excellent idea of exactly what are you looking at here. Right. Okay. So for example, yeah. So that's one experiment you can do. So for example, if you're looking at, say you have a part of an aircraft wing, where you've got a crack, okay, there's different stress patterns involved in the formation of that crack. If you look at the diffraction pattern you get at each spot, that enables you to map, well, is the crystal structure being compressed? Is it being expanded? That enables you to map the stress. And then you think, well, it's another contributing factor as to where the crack occurs, migration of trace elements within the metal that the wing was made of, and you get a picture. Well, here we see the stress map. Here we can see where the elements are. Looks like the elements have migrated to a certain point. That's nucleated the crack through this stress field, and you start to understand, well, why did this particular piece of material fail under these conditions?
Okay, so is that an actually practical example of something that could be done then? At the site where you bring in a piece of metal, say from an aircraft wing that is fractured, put the sample in the beamline and assess it that way. So what you just described is actually done.
Yes, that's exactly the kind of thing you can do.
Very interesting.
But that's just one small area.
Sure, yes, of course.
So Rob, my question is, with a diagram such as we have here, is there a job for Colin Jagoe at the Canadian Light Source, or are we in no danger of losing him?
I don't think there's any danger of me going up there anytime soon.
No, not in drafting.
Perhaps not in, perhaps not in our CAD division, right?
Well, I think you did a great job. Thanks, Colin. Good support. Thanks for walking through that, guys. Let me see if we can get this down here.
Okay. Oh, and it's now Colin Synchrotron, is it? Nice.
Of course.
Nice.
So, well, that was fun. Tracy, you do a lot of the educational outreach, as I understand it, at the Canadian Light Source. Maybe you can talk a little bit about those programs. I'm sure there'll be lots of teachers listening that'd be interested to know what kind of material, what kind of resources you can provide or help them with.
Well, there's probably 4 things that the teachers and the students in this audience might be interested in. One is that we do have a fair amount of materials available online. And so that's on our website, which is www.lightsource.ca. And you'll find a teacher's guide there. You'll find posters that give you lots of examples of research that's gone on, a couple of videos, things like that. Secondly, for teachers that want to know a little more about CLS and how it works and sort of get involved in things, we run a workshop in October. And there's information for that online. And at that workshop, teachers get a chance to go down on the beamlines with people like Rob and collect data and actually participate in experiments, and then get lots of tips and tricks for how to bring this science information back to their classroom and their students. Now, in connecting students to this kind of research, there's 2 programs. One is video conferencing, much like this. And what we're doing is we are still developing those programs, and what we'd like to do is to connect with teachers so that we can specifically work with you on something that you're looking for to fit your curriculum. So it might be an interview like this. It might be that we want to go down on a beamline and see if there's an experiment to observe or talk to that researcher. It might be someone in our engineering department or our physics department that you want to connect with. There's lots and lots of opportunities, and I'm happy to work with the teacher to figure out where we can make those connections.
Just a quick, from a practical point of view, you talked about, you just said, we could go down on a beamline and take a look. Yeah, my first question is, are you guys equipped with sort of the portable video type equipment where you can actually manage that and take it right down into the room where the equipment is?
Yeah, I'm talking to you on a TV monitor that is on a cart with wheels that I push around the facility and hook up where I need to. And we have, for example, we did a series with a grade 8 class out of Calgary, Alberta last year, where we introduced light and optics to them ahead of time, and then we went down on a beamline and worked with an archaeologist who was looking at stone tool sources, so the rocks that ancient peoples would have been cutting stone tools from, and she explained what she was researching and how it all fit. And then we came back into a room like this and went through for the students exactly what was happening at the sample level, at those electron shells in order to collect their data. So that was a series that teacher and I worked out, specialized for his curriculum.
Very much fun is that.
Man, okay, that's very cool. Very cool.
Yeah, It's interesting stuff. And the last one that I'd like to tell you about is also very cool, and it's called Students on the Beamlines. And what we do with that is small groups of high school students will form a collaboration team with researchers like Rob and their teacher and sometimes other subject experts from universities, and they design their own research. And they get to come here, conduct their experiment, collect their data, analyze it, make presentations. They become synchrotron users. And it's not a demonstration. It is actual research that sometimes has been published within the scientific community, depending on what they find and what they're researching. It's really exciting.
That is very exciting. Just last weekend, we were in Ottawa at the regional science fair, as one of the lead-ups to the Canada-wide, and we were commenting on the connections that some students have with research facilities. And sometimes it's as simple as, mom works at a hospital lab and they can get in there and do some really neat things. And then you have the kids that don't have access to those kinds of things. So what you're describing sort of opens it up to anybody who has the interest in something that could be done at your facility to be able to do that. So that's very, very exciting.
There was a young lady at the Ottawa Science Fair last weekend that had actually come up with a design to make stairs more safe for the elderly as they ascend or descend. And she was so successful with it last year that she actually had it incorporated into the building code.
Fantastic.
Beyond, but and so that's the first thing that jumped into my mind when I heard you say they can come and perform, not just have fun for a day. They're actually doing experiments and real research there, which is phenomenal. Just going back.
As a matter of fact, a couple months ago, you had a conference with Appleby College.
Yes.
They are working on a Students on the Beamlines project. That's what their request to you to interview, I forget his name, but he's a researcher into brain cancer.
Yes.
That was part of their research. They wanted to take a look at, what happens at the cellular level as cancer and things like that. And when they were doing research to understand what was happening in order to design their experiment with us, they had requested that video conference with you. So they will be coming here in May.
That's very cool, because I remember, obviously I remember the video conference, I remember asking them questions, and I remember their questions were about sort of the interaction at the cellular level. And in the back of my mind, I'm sitting here going, how are they working on a project like that? I wish they told me what they were doing, because it all makes sense now. That is so amazing.
Yeah.
It's so cool.
Yeah.
Tracy, how many students can you hope to accommodate in the different programs that you're running throughout the year? They sound very, I don't want to say time-consuming.
Personalized.
Personalized, yeah. How many can you hope to incorporate their necessities?
Well, with the video conferencing, obviously we can reach more students and sort of do a little more with that than we can with Students on the Beamlines. Students on the Beamlines is the kind of program where you sort of sacrifice breadth for depth. You don't, it's really designed for students that are very, very curious and who really want to get in there and try doing a little bit of research. It is a lot of time and a significant amount of work, but there's a lot of reward there as well. And then with video conferencing...
I just wanted to say the one thing, and I've heard people say this before, sacrificing breadth for depth. I'm not convinced it's a sacrifice. Right?
Fair enough.
When a student gets so deep and understands something so well, that's what real research is. Researchers have a depth in a particular field, so it's in no way a sacrifice. It's a wonderful thing that you're doing.
Yeah, it's a really fun program.
Yeah. And then the second one you said, sorry, with the numbers of kids?
Well, with video conferencing, obviously you can connect more students to research sort of in a faster way, but as you mentioned, it's much more of an introduction, sort of hopefully get them excited about it. One of the real strengths that I can see about synchrotron science from an education perspective is that it's very multidisciplinary. It's not unusual to have a team of researchers come that involve chemists and biologists and physicists all working together, approaching the same problem but from different angles. Yeah. And that's really nice to show students. And then the other part of it is, like I said, realistically, every field of scientific research taps into synchrotron or can tap into synchrotron research at some time. So it really doesn't matter what subject area you're teaching, there's probably a connection. There's a lot of, I find our students, our Canadian students, are interested in an awful lot of environmental research and health research. And so there's a lot of exciting topics to discuss within that.
I do want to take a quick break, if we can, for a couple of minutes while I do a sponsor spot here. I don't want to forget our good friends over at Mueller Systems. When we come back, we'll have some more questions for Rob and Tracy. Stick around, folks. We had a very interesting discussion here today, and we certainly appreciate your time. Mueller Systems out of Woodstock, Ontario is that organization that offers your organization, or you personally, a backup solution for your computer environment. So whether you have Macs, whether you have PCs, whether you have network infrastructure, we all have data that we need to protect. The best way to protect that is to have some type of an offline backup service. And that's what Mueller Systems provides. And of course, just recently, we all know the disaster of when I tried to play home plumber in my house, and we had a 2 or 3 inch water issue and fried out a computer. First of all, get those computers off the floor. I definitely recommend that. Secondly, when your husband tells you he knows how to fix a pipe, don't believe him and just call a proper plumber.
Particularly if you're that person.
Particularly if it's me, because otherwise you're in big trouble. But third, make sure you have that offline backup. It's going out there in the cloud. We don't know where it is. Maybe it's going over here to the Synchrotron. We don't know. It's out there somewhere. The moral of the story is get an offsite backup. If you go to their website today, which is muellerdata.com/VROC, MULLERDATA.com/VROC, you'll be able to download and install their software free of charge for 90 days, which is tremendous, really. I don't know of any company that allows you to do it for 90 days. It's always 15 or 30. But 90 days, that'll give you a good idea of whether or not it's going to be the right fit for you. So we do thank them again for their support. muellerdata.com/VROC. Okay. Coming back to the Canadian Light Source with Rob and Tracy, Colin.
Yeah, it struck me again as Tracy was speaking, and I'm pretty sure you two will agree to this, but I want to maybe get sort of Rob's perspective on it as sort of the background of a working scientist. And this has come up in so many different podcasts that we've done. The interdisciplinary nature that science really is. Like when you talk about introducing optics to grade 8s and then bringing in an archaeologist to talk about what they're using that for, I'm just sitting here going, wow, that's so cool. And then obviously, Rob, you know what's the physics of the light source is only the starting point to then what's being discovered in all these different areas. So maybe just give it, maybe it's just your thoughts on sort of how science teaching probably should be, maybe, I don't know, more interdisciplinary rather than the defined subjects that we have now. Because every time we talk to researchers, those subject lines are blurred. They really are. So I just, maybe, as a working scientist, what do you think about that sort of, traditional way of going about science education?
Yeah, I mean, absolutely. I mean, you hear this term, diversity is strength. And this is as true in science as everywhere else. Because in some ways, yes, you need everybody to be interdisciplinary, but you still need people to have a particular perspective. So when you're working on a problem, you think, okay, somebody with a chemistry background has a different way of looking at the world than somebody with a physics background or somebody with a biology background. And if you bring those different backgrounds into solving a problem, then you've got a much better chance of getting a solution. And a lot of science really is problem solving. So,
yes.
So for me, this is extremely important. The traditional academic boundaries, we started to see those really being broken down in the 1980s at the university level, where people stopped saying things like, I'm a physicist, so nobody else's opinion is of any value. The old thing, everything's physics or stamp collecting. That kind of attitude is going away simply because you end up working at a place like a synchrotron. If somebody can help you with a problem, you start to respect, well, okay, you're not a physicist, you don't think like me, but your way of looking at the world helped me solve my problems. So the thing I would like to sort of say to educators is, be proud of your discipline and instill the ethos of your discipline, but don't shut everybody else out. Don't be an arrogant physicist, don't be a closeted chemist. Don't be a, I'm running out of adjectives here, right? You get what I'm saying here, right? And then if you pull in the second order effects of, yes, you have chemists and physicists and biologists, and then you have people from different cultural backgrounds bringing that, because you have two physicists from different cultures, a Japanese physicist, a European physicist. We look at the world in slightly different ways. Once you begin to work at an institution like a synchrotron, where you have people from different disciplines and people from all over the planet, you have the perfect storm of problem-solving capabilities. And especially think, we have engineers here, we have agricultural scientists, we have the University of Saskatchewan right next door, full of people who are quite happy to help you with your problems. And that is the real power of a facility like ours, is not, yes, we can do cool stuff, because science isn't done by equipment, it's done by people. It's like you might be down working on a problem at 3 a.m. and there might be somebody on a neighboring beamline you've never met who has an insight that can help you. That's the huge benefit of these facilities.
It's the kind of place where the lunchroom conversations are just amazing.
Yeah, absolutely. A little bizarre sometimes, but yes.
Hey Rob, if I'm a member of the general public and I want to take a little trip in the summertime and drive out to Saskatoon, do you guys run tours for general public, or how does that work?
Well, actually, I'll pass you over to Tracy, because that's actually Tracy's department to run tours. The short answer is yes, we do run tours. And how many people do you get?
Here's Tracy's phone number.
We average probably 5,500 people through the facility in visits per year. Now that's some public, that's about 3,500 school kids on tours, and that's also a lot of government and researcher tours as well. Your best bet is to phone 306-657-3500. That's the main line, and the receptionist will be able to redirect you as needed, or contact us over our website.
And what's your home number again, Tracy?
No, thank you. But yeah, we do. There's a lot of interest in the facility, and we're happy to share our excitement for science with anybody.
Yeah, I'm wondering about school tours now. What sort of grade levels tend to come through, and what are the kind of focus of the visits for different groups?
It's pretty similar to what I mentioned with the video conferencing. For visits here, we accommodate grades 5 and up, because in the Saskatchewan curriculum, and realistically that's who's coming in for tours, in Saskatchewan curriculum at grade 5 is when they really get into an understanding of the atomic model and sort of different molecules. And if they don't understand what an electron is, then what they see here is concrete and cables, and it's too abstract for them without a lot of lead up.
Sure.
So realistically, grade 5 and up, they get to walk about the facility. Then we do some hands-on activities with them where they build a monochromator, which is the device that selects the wavelength of light. They get to build one using rainbows and prisms and select blue. Things like that, and take a look at equipment and talk about the research, and sometimes meet some of the scientists.
I'm thinking that, in your household, Colin has a daughter that's, I think, 7 or 8. 7. And lo and behold, she's interested in science.
Imagine that.
I think I see a Winnebago in your future.
Not with $1.30 a liter.
Yeah, buddy.
Yeah, no kidding. I'll get my 11-year-old to give her a tour.
That's right. Perfect. Hey, Tracy, just on the video conferencing program that you offer, are you finding that you're doing most of that within Alberta, or are you actually expanding to other parts of Canada, and are you doing anything overseas with that?
We haven't done much overseas in terms of educating with schools. We've done some connecting overseas from synchrotron to synchrotron for collaboration purposes. Sure. So it is possible. When we're really trying to expand our video conferencing capabilities. As I mentioned, we're new to that, so we're still learning and building that program. So across Canada, if you're a teacher that would like to connect, contact me. Over our website is probably the best way to contact me, and we'll work something out.
Sounds great. We can probably help you with that, since that's a large part of what the VROC program is all about. I'd be happy to help you connect with some students and teachers and whatnot.
That would be fantastic.
For Rob and Tracy, before we let them go and bend some more light.
Go bend some more light. No, nothing comes to mind right now. This has been a very fun conversation.
This has been wonderful. Thank you both for coming on the show today. Really appreciate your time. And let's give that website address again one more time for folks who might be listening.
www.lightsource.ca. And thank you guys. This has been great. I've thoroughly enjoyed this.
Yep, thanks very much. This was fun.
It's our pleasure. If you can talk Colin through how to draw something, I'm sure you can talk anybody through it. So thanks a lot, guys. Really appreciate it, and have a good day. And until next time, this is Kevin Cougler on behalf of my good friend Colin Jagoe saying thanks a lot for tuning into This Week in Science and Education. We look forward to talking to you again next week. Have a good week, everybody.